This is two-sample t-test, and the test is for the difference in the mean between the two samples. So the null hypothesis is that the two means are the same. The alternative hypothesis is that the two means are different. We can also have a one-tailed test above or below. Mostly these are for test of the mean being equal. For the two-sample t-test, we have two samples that we are comparing rather than one sample that we're testing for a difference from a mean. And in this, there are two kinds of two samples. The first are independent samples. We have one sample where we're testing a process, and another sample we're testing another process, and the two aren't linked in any way. Inside of this, there are two sample types. The first is one with equal variances, equal standard deviations between the samples, and the other is unequal. And we'll do them both, but the good thing is that there's not really a problem with this, because if we always use unequal, we will have the equal situation covered. The other situation is if we have paired observations. And this can be a before and after, for example. We have some people that perform a physical test, then we do physical therapy or some kind of treatment, and then check again and see whether the before and after are different. For this, we're going to need data from MyOpenMath. And in here, this is the data from OSCIL. This is an old text that has some problems in it. And I'm going to download that and open it. And there are two pages. There's a wire load page. This is a test of independent samples. And the next page is the Brinell test. This is a hardness test, and it is a paired observation test. We'll do the independent samples first. For this, we need to have the data analysis ToolPak loaded on your computer. And if you have a Mac, this isn't going to work because they don't have the data analysis ToolPak. So you have to get on a PC somewhere, and in File, go on to the left-hand menu. At the bottom is Options. And at the bottom of that, we want add-ins. This is a list of the add-ins that Excel has. They're programs that are present, they're just not turned on. And we need to make sure that the Analysis ToolPak is added. If it isn't added, click on it and then go, and it will show up on the list as highlighted and it's ready to go. So there's not much to do there. Say OK. And then here, if you go to the Data tab, the Data Analysis ToolPak shows up on the top right. And the Data Analysis ToolPak is a list of statistical programs that Excel has built in but are not turned on unless you have the Data Analysis ToolPak running. We want to go down the list, and there are 3 t-tests. The first one is the t-test for paired two-sample, which is the one with the matched pairs. The second one is the two-sample. These are independent samples, assuming equal variances. And the third is the same thing, assuming unequal variances. We want to do 2 sample assuming equal variances first. Click OK, and you get the typical dialog box which says this is what data to use and this is where to put the results. So that for variable 1, click in there and then mark process 1 observations. For the second sample, same thing except mark those observations. Other things in here are labels. If we did this, we would include the process 1 and process 2. The alpha level can be adjusted. It defaults to 0.05. And the output range comes up. If you don't do something different, it will put it on another worksheet. We want to keep it on this same page, so I select the output range, click on the arrow, and I'm going to put these results right here on this page. From there, all you do is say go. There is nothing to calculate in this. The computer does absolutely everything for you, and it gives you all of the pertinent information without any excitement whatsoever. You don't do anything. And I'm going to knock some decimal places off of this. Here, the t statistic, the calculated difference between the two means, is minus 2.44, which indicates that the process 1 mean is less than the process 2 mean, since it's negative. And in these parts of the table, these are the critical values and the p level for the actual test. So for this first one here, this is the probability that it is less than t. This is a one-tailed hypothesis. This would be that the critical region is to the left, and the 0.017 is less than 0.05, so we would reject the null hypothesis. Also, if you look at it, the critical value for the t-test is 1.796. Our t-statistic is less than 1.796. In this case, we're dealing with the lower end. It's minus 1.796. This will always show up as positive. So if you have a left-tailed test, you have to change it to negative. The degrees of freedom is a complicated calculation in some instances, and all you need to do is take it off of this table. You don't need to calculate anything. 11 degrees of freedom for the test, and if we go into t.inv and look up 0.05 equals t.inv, and for a one-tailed test, this is 0.05 in the left tail, 0.05 with 11 degrees of freedom. We get the 1.796 that's in the table, except it gives us the negative version since we are on the left side. For a two-tailed test, we would have the same thing, t.inv, except now we need a 0.025 because we have 0.025 in one tail, 11 degrees of freedom, and there's the minus 2.2, which is the critical value here for the two-tailed hypothesis. I'll open this up a little bit. The names are obscured. Critical, two-tailed, and the p-value for 2.02, and the value cut off by minus 2.44. So we have a line, 0, minus 2.44, and we're looking for the actual position of this. If you go into t.dist in Excel, we go into t.dist in Excel equals t.dist. We get minus 2.44 with 11 degrees of freedom, and we need to put in cumulative, put a 1 on the end, and the cutoff value for the p-value for one tail is 0.0164. This one has 0.017 because it's a slightly different calculation between what's in the table and what the t distribution calculation is. And if we did the same thing for the two-tailed hypothesis, we would get 0.033 as the cutoff value in the tail, so that all the information for the test is right there in the table. No calculations required. So minus 2.44 is to the left of minus 1.796. So we would reject if it were one-tailed test on the left, and 2.44 is less than minus 2.201, which would be if it were a two-tailed test. So we're still outside of that, and the result is to reject the hypothesis that the means are equal. We're going to do the same test assuming unequal variances. And the only point of this is to show that there's really no difference between two sample assuming unequal variances and two sample assuming equal variances, except that the unequal variance case will handle more extreme situations. If the two variances are equal, the results will be the same as using the equal variance test. So back to data analysis. Now we want two sample assuming unequal variances. Do the same mark, process 1, process 2, and I'm going to put the output range just below the table that we have, and we leave the alpha level the same, and this is assuming unequal variances. Take some decimal places off. And in here, our t statistic is 2.43, where it was 2.44 previously. Instead of 0.017 for a one-tailed significance level, we get 0.02, and 0.03 for the two-tailed test, so that they are different, but they're not different enough to make any difference. We still reject the null hypothesis, and all the calculations are the same. So that always use the two-sample assuming unequal variances, and it will handle the equal variance case just as well, and we'll come up with basically the same results. The second kind of test is for matched pairs, and this data is for a hardness test. A Brinell hardness test, they take a small ball and push it into a material to see how much the material deforms. And the harder the material, the higher the Brinell test number will be. In this case, we have an A and a B ball. It's as though we have two manufacturing plants. We want to make sure that our results from test are the same, so we're testing whether these two balls that are used in the test are the same. So this is, say, A and B, and we're using the test on the same material in both instances, so it's matched. So if we're using some grade of aluminum and pushing this ball into it, that same grade of aluminum is used in the first test and in the second, so that they are paired observations. Now there are two ways to do this, and the easy way is to go back to the Data Analysis ToolPak and go down, and we want paired two-sample for means. And the setup is exactly the same as before. I'm going to put the observations over here to the side a little bit because we have another way to approach this. But we have the first column, the first sample, and the second sample. I'm going to put the output right there. Same alpha level, 0.05, and the hypotheses are the same. You can do the means are equal or they're not. Click OK, and here is the sample result. The means for each of the two, the variances for each of the two. This is just the square of the standard deviation. The number of observations, but here the number of degrees of freedom is 14, and this looks like 15 minus 1, but it really isn't. There's kind of a complicated calculation that goes into this, so you don't really need to know about it. You just need to look at the table and see what the degrees of freedom are. Don't need to calculate it, no need to calculate a t-value of any sort. So here, the result is that the t-statistic is 2.810, the test difference between these two means. Because it's positive, if we were doing a one-tailed test, this would be a right tail, so that the number we would compare the paired test to is up on the upper end. So our 0.05 was on one end. If we're doing it as a two-tailed test, we have half of that on both sides. And from the table, the critical value for a one-tailed test is 1.761. So this would be 1.761. And our t-value is 2.8, so it's way out here. So we are rejecting regardless. If it's a two-tailed test, for the difference in means is the same versus it's not, the critical value is 2.145. So we have 2.145 on the upper end and minus 2.145 on the lower end. And the 2.8 is still way out on the far end, so we're going to reject in either case. So this one, the null hypothesis would be that mean of 1 is less than or equal to the mean of 2, and the alternative is that the mean of 1 is greater than the mean of 2, which points to an upper-tailed, one-tailed test. For the two means being equal, it's just the mean of 1 is equal to the mean of the other, versus the mean of 1 is not equal to the mean of the other. We have a two-tailed test. All this information is on there. There's a 1.761, the 2.145. If we look at the p-value for the test, it's 0.007. So if we looked up 2.810 in the t.dist command, we would get 0.007 on the upper end. So the 2.8 is 0.007. The actual return command would be, here it would be 0.993, and 1 minus that is 0.007. For the two-tailed, we have the same probability in the tail, 0.007, but since it's two-tailed, we have to add the other end, 0.007, which gives us the 0.014. So it's just 0.007 doubled. Always double it when it's a two-tailed test. The other way to approach this is to calculate the difference between these two values and then use a regular t-test to test for a difference. So in this one, it's equals the first minus the second, and we repeat that calculation on down. So we have the difference between the two observations. And it doesn't matter what order you subtract them in, you're just going to get a positive or a negative if there's a direction to it. But the rest of this, we need the average, the standard deviation, and the standard error of the mean. So the first is the average, and we want the average of the differences. And the average difference is 8. The standard deviation of the differences, STDEV dot S, and the standard error calculation is the same as always, standard deviation divided by the square root of the sample size. So we have standard deviation divided by the square root of 15. And the standard error of the mean is 2.84. And we have, again, more decimals than we ever need. We'll make it 2.847 so that our test statistic for this difference between the means is going to be 8, and this is a t-value, 8 minus the hypothesized value, the difference is 0, divided by the standard error, which is 2.847. So I'm going to find out how far 8 is from 0 measured in standard error. The result of that is 2.81. We are 2.8 standard errors above 0, and this is basically the same number that we get from the paired test that's automatic in the data analysis ToolPak. So that all of the same things would apply if we're using a two-tailed test. The critical values would be 2.145. One-tailed test, the critical value is 1.761. And in either case, the mean difference, t statistic, is 2.81. So it's still inside a critical region, either one-tailed or two-tailed. This is a way to do the test. Get the difference and use the usual t-test with all of the calculations involved, or you can use the data analysis ToolPak and it does it all immediately. There's no waiting for an answer or no calculations required. So either one of those things will do. So that's the two-sample t-test. We have independent samples with equal and unequal variances. And we have the paired t which we're testing two samples on the same thing. We have a reason to pair the observations. Excel will do all of these. There's no need to do any calculations. The important thing is, can you interpret the results of these tests?